welcome everyone to today's speaker series. We are Design++, and we host this speaker series, the seminar series, every semester. We have a common Zoom link, which you can check into, which you obviously found. And this is our speaker lineup for this semester. And we are over halfway through after today. And we still have 2 more talks for the final, to finish through the rest of the semester. So as you may know, we have a YouTube channel where we record and keep all of our talks. So if you've missed some, or if you have to leave early, then you can also check out the talk later. The 3 of us, so Michael, Romana, and I, we host and organize a lot of activities in Design++. And so feel free to reach out to us if you have any questions there. But the most important thing for today is to introduce our speaker. The talk today will be on interfacing machine learning tools for creative users. And I'll introduce Ardavan Bidgoli. He is a robotics fellow at Carnegie Mellon. So I will just say a few words about Ardavan. He's a computational designer, roboticist, and machine learning researcher. His research concerns the interfaces that enable designers and creative users to interact with computational design tools. He's currently doing his Ph.D. in computational design at Carnegie Mellon in the School of Architecture, studying affordances of situated approach to machine learning and creative computing toolmaking for domain expert users. He is also the lead instructor of the Inquiries into Machine Learning and Design course at CMU, the School of Architecture. His industry partnerships span over various research and products teams in the AC tech companies, including the Generative Components team at Bentley Systems, as well as Autodesk's OCTO team in Pier 9 and Build Space Facilities. Ardavan also holds a Bachelor of Architecture and Master of Architecture from University of Tehran, and a Master of Architecture in Design Computing from Pennsylvania State University. So also check out his website if you want to see more. And with that, the floor is yours.
Oh, thank you very much. And thank you for the kind intro. I think it was pretty comprehensive and it eliminates the need for the slide that I have in my presentation. So let me just start this presentation and make sure that everybody can see it. Is it good?
Yes, it's great.
So first of all, I just want to thank you all for joining us today. If you're joining us in the United States, good morning. If you're joining us from Europe, good afternoon, and anywhere in the East, good night. And first of all, I want to thank Design++ team and Danielle and Michael for inviting and organizing this event. It's my great pleasure to share some of the work that I've done recently and get a broader audience about the type of work I'm doing and the type of research that I'm right now conducting. As she kindly mentioned, I'm Ardavan Bidgoli. I'm a Ph.D. candidate in the Computational Design program here in Carnegie Mellon University in Pittsburgh, Pennsylvania. And as she mentioned, I'm holding a Bachelor of Architecture, Master of Architecture from University of Tehran, and I came to the US in 2014 to get my MArch in design computing. Yes, they call it design computing in Penn State, and computational design at Carnegie. And I've been teaching machine learning and design for the past couple of semesters. Before that, I was robotic fellow and I was teaching architectural robotics to students here in the School of Architecture. And during the past couple of years, I was working with Autodesk Octo team, which is the research branch of Autodesk that's aiming towards exploring the new possibilities on the long-term horizon of the AEC industry. I worked with the robotic lab at Pier 9. Some of you might be familiar with that team. And I was also working with the Build Space in Boston. Before that, I was an intern at Bentley Systems. So if you're familiar, Bentley Systems is making microstation and generative component products, and they are actually in Pennsylvania, United States. And if you want to contact me after this lecture, you can either send me an email or checking out my website. So before getting into the discussion of today, I just want to clarify a couple of things that are basically going to be an overarching theme in this presentation. So I want to clarify.
I want to interrupt quickly. Someone said that the volume is somewhat low.
Okay, is it better right now?
That sounds better to me, yes.
Okay, so I'm going to keep this microphone closer to my mouth and also increasing the level of sound here. So good. So I just want to clarify some of the terms I'm going to use. And these are not definition. These are actually a kind of defining the scope of discussion today. So I want to say what is an interface that I'm talking about today and what is ML-based, what does it mean, and what type of computational design tools I'm talking about. So first of all, let's start with interfacing. What do I mean when I say interface? Basically, when we say interface, we usually get our mind directed towards graphical user interfaces, these shiny buttons on our computers or on the mobile phones and etc. But interfacing in the title of this lecture is actually referring to a broader point of view. It's covering all the interactions in different capacities that happens between a creative user, a tool maker, and its tool through the process of making a tool, customizing it, or even using it. So all these interactions between the tool and the user, I'm referring to them as interface. And when I say ML-based, I want to refer to a bunch of tools, computational tools that are using machine learning algorithms, either in the backend or in the front end, doesn't matter. Mostly today, I'm going to talk about the machine learning models in the backend. And these models can be discriminative, generative, making new samples, or like deciding if this is going to be from class A or class B, or predicting the behavior or something. But powered by ML, I mean that at the background or in the front end, there is a machine learning algorithm that facilitate the process rather than the conventional computational methods that we are using. And I want to today talk about a specific group of computational tools. Computational tools are all around the place right now. For every practice we have them. We have computational designs for analysis, for simulation and everything. But specifically today, I'm going to talk about computational tools that creative users are using in their day-to-day life and practice for performance art, for design, and for making. So these three terms are helping me to actually define the scope of this discussion for today. And because machine learning is the ML word of the day and everybody is using it, it seems like a buzzword, but I think it's necessary to just clarify what's happening here and what do I mean by machine learning here. So machine learning is basically a subcategory of artificial intelligence, and there are different definitions of that one, and I think it would be a good idea to have a look at the classic definition of machine learning. As Tom Mitchell mentioned in 1997, a computer program is said to learn from experience E with respect to some class of tasks T and performance measure P. If its performance at tasks in T as measured by P improves with experience E. And this is a really, really complex way of saying something like this. Machine learning algorithms are algorithms that can learn from data. And this super simplified definition is coming from the one and only Ian Goodfellow, who's the person who invented GAN architecture, which is the one that so many people are using right now. And it's coming in his book, Deep Learning, which is a really good book if you want to get into the technical side of the machine learning. So basically, it means that a machine learning algorithm and a machine learning workflow, it doesn't need to be explicitly told how to solve a problem. Instead, it receives a bunch of data, it explores the data, and it tries to figure out what are the relationship between the elements and find a way to actually find a solution, an algorithm to solve that problem. And you may also hear a lot during this presentation that I'm talking about machine learning algorithm. A machine learning algorithm is a kind of assembly of 4 different elements. So this is not a world agreed upon categorization, but this is the way I'm defining things to make it a little bit easier to understand. A machine learning algorithm is a kind of combination of a data set that's either being downloaded from a server, it might be created in real time, or something that you by yourself created, as I'm going to discuss later on. And it also has a learnable model. When you hear something about artificial neural networks, deep neural networks, I don't know, convolutional neural networks, recurrent neural networks, they are all learning models, which are basically, they are tunable functions that can be combined with a cost function to look at a data set and figure out if they understand what's happening on that set of data, find its distribution, or find out how they can distinguish between them. And in order to optimize this workflow and reduce the loss or cost function, we use an optimizer algorithm. If you have heard about ADAM, RMS prop, stochastic gradient descent, these are all the technical words that are happening here. So whenever in this presentation I'm talking about the machine learning algorithm, I'm referring to this big image, the data, the learning model, the cost function, as well as the optimizer algorithm. So when we combine these all, we can actually use the machine learning algorithm, train it, and then put it in the backend or front end of our tool. Just to make the whole discussion a little bit more tangible, I'm going to show one project from back in 2018 when I just got introduced to machine learning, and I was super excited about what are the possibilities, what are the things we can do. So in this project back in 2018, I was working with my colleague and friend, Pedro Veloso. By that time, he was also a PhD student in the program. And we were attending a class at CMU that was about art and ML, or I think the official name was Art and AI. The class was running by a professor from machine learning department, a professor that was joint appointment with the computer science school and School of Art, and also Golan Levin, which is the one and only art director of the Studio for Creative Inquiry. And we started to see these machine learning algorithms, the generative models, and we were thinking how we can use these machine learning algorithms as a design tool for creative purposes. So we came up with this idea that maybe it's possible to repurpose one of the really interesting algorithms that we found and somehow tweak it to convert it into a design tool. So there was a project called Latent 3D Point, and it was developed by researchers. The lead researcher was Epanos Arkliotas, I hope I pronounced his name correctly, and his colleagues. And what they were doing was pretty interesting. There was a big data set called ShapeNet, and this data set is containing hundreds and thousands and thousands of 3D objects categorized in different classes. For example, chairs, cars, tables, whatever, and they are all 3D objects. In Latent 3D project, they actually convert that data set from mesh geometries into point clouds, and then found a way to learn the distribution of data. And then they decided to test various machine learning models and see how they can do with them. And the one that actually caught our eyes was an autoencoder, which is a pretty simple architecture. Back in 2018, when we were looking at this model, it was complex for us, but it's right now one of the simplest models you can find out there. But the autoencoder model here is pretty simple. The concept was pretty simple. You input a piece of data, for example, a point cloud of a sphere, as you can see here, and it tries to convert it from high dimension. For example, here it has 2000 points. Each point has XYZ, which means that each piece of data here has around 7,000 pieces of information. And it tries to compress this data into really, really small dimension, only 32 numbers. It's going from 7,000 numbers into 32 numbers. And then it tries to reconstruct it back. Looking from outside, it seems pretty useless. You have a piece of information, you try to compress it, and then you get it back on the other side. And as you can see in this image, it means that you are going to lose some information. The sphere that I have at the end is a little bit fuzzy. It's not as accurate as the one that we have at the beginning. But there is something really interesting here. This machine learning model actually makes a specific representation of that 3D object and its hidden layers at the middle of the model where we cannot usually access or understand. So that layer is called latent space. And this model can get a high dimensional piece of information, map it into that small dimension, and then get it back. We realize that it's actually possible to start playing with that latent representation, just tweak it a little bit, and then push it towards the decoder part of that model and see how much effort it's going to put there in order to make sense of that piece of information that we give it to this model. Just think about it this way. When somebody describes something to you, it means that it's thinking about a really complex entity, for example, it's trying to describe you the landscape of a city, and then it just do it with a couple of words. And then your brain is going to go through those couple of words and try to reconstruct the landscape of that city based on your internal understanding of those words. This is something similar happening here. So those 7,000 pieces of information mapped into 32, and we said, let's play with every single value in that 32-dimensional vector and then pass it back into the decoder model. So this GIF here actually shows what will happen when you individually change those numbers. And I want you to actually have a look here. If you see my mouse, it's the second row from the top, the third column. So here you can see that just by changing that value a little bit, just we're changing it with like 0.1, 0.2 or something, the model adds a handle to that chair. We didn't define this. We didn't intend to do this. The model by itself figured out there is something called handle. If you give me this signal in this direction, I'm going to add handle. And if you look carefully at this GIF, you will eventually find like there is one that actually controls a number of legs. There is one that controls the opening in the back. And all of these, vectors are working in a way to change the final design. So Pedro and I said, okay, it's actually a good idea. It's a potential for making a design tool. So we interface the machine learning model in the backend, and we train it on the cloud using the script that was provided by the researchers. We just downloaded we cloned the GitHub page that they had, and we uploaded on Amazon AWS and trained the model and, downloaded the trained model, put a nice interface around it using Django interface. And then we packed it as a design tool for a user. And that user didn't need to deal with any of the machine learning shenanigan at the back. It was just an interface using a mouse and a MIDI mixer, which is something that you see with DJs and music makers, to play with that latent space and get the desired result. So the interface was something like this. The person could say, I want to play with chairs, could select one initial point, and it could get some information about what will happen if you change those sliders on those MIDI mixers, and it could work like a magic black box. So I want to distinguish between the role that me and Pedro played as toolmakers. We interface the machine learning model through coding, training, running the distributed training on cloud, and the end user, which was just dealing with this literally black interface in which that person wouldn't know anything about the machine learning in the background. It just plays with these sliders and make these new models. And as a cherry on the top, we actually got the exports from this model, 3D printed them. They are actually back here behind me. And the results were pretty interesting. I really enjoyed it. So here you have noticed that I talked about something about a black box model approach to machine learning that end user was working with. And we also playing a kind of like a more direct interface with the machine learning model in the background. And there's a kind of like cascade and a kind of like a gradient between these two approaches. And there are so many different approaches to this one. For example, there are so many people who might be more interested in interfacing machine learning models just as a black box. If you have recently used Photoshop actually added a lot of filters and features that are completely based on machine learning, but you do not engage with the machine learning side. You just use that filter. It selects the boundary of a human face, or excuse me, it can actually convert a face that's a little bit gloomy into a happier face. Definitely try it. It's pretty nice. You don't need to do anything with the machine learning. You just interface a familiar workflow and familiar platform called Photoshop, and it's just a new filter there. But there are some other people who are a little bit more towards toolmakers rather than just the users. And they are thinking about, what if we retrain this model and repurpose it for the type of work that we want to do? I think Pedro and I, in the last project that I discussed, were just walking into this realm. We didn't have that much of experience. We didn't know how to, for example, work with that specific version of, I think they were using a really awkward framework that we were not familiar with. But we realized that we can use the scripts and the tools provided by them to repurpose and retrain this model to work towards the purpose that we were looking for. There are also other people that I'm actually a little bit leaning toward this direction that are going one step further. They not only train the models, but also adjust them, fine tune them. There are some people who are making their own data sets to fit these models with, and that's really interesting workflow. So many projects that we see recently using GANs and pix-to-pix in specific are actually following this approach. So a little bit deeper into the interfacing the machine learning model rather than just the interfacing the black box workflow. And then there are people who are developing their own models. They're not just using off-the-shelf models. They are making their models, developing their own data pipelines, and finding their ways through it. And then there are researchers in the machine learning side. They are inventing new models. So if you have heard about GANs, if you have heard about variational autoencoders, there are people who actually invented these models. These people are usually researchers in the field of machine learning or computer science, switching to machine learning, and they are making these new tools and methods. And then we are actually taking advantage of those models and make them suited for our workflow. So as you can see, there is a kind of like gradient of machine learning skill and knowledge that you need to have in order to go down this ladder and get closer and closer into making the tool for yourself rather than just using something that somebody uploaded on the internet. So there are a couple of requirements, and there are some things that happens if you want to go across this spectrum. For example, using black box model usually means that you're going to be in your user-friendly interface and you're working with your familiar tools and platform, like, as I mentioned, Photoshop. Or if you have worked with something called Runway ML, which is pitched as the Photoshop for machine learning models. It's basically, the interface is just like Photoshop, something that we are completely familiar. We use it on a daily basis. And it's really easy for us to adopt it and start using it. Imagine that if you had really, really reliable, fast, and efficient methods to implement machine learning models and machine learning algorithms in Grasshopper, like I think 9 out of 10 of us would actually jump and do our experiments right now, not even tomorrow, but right now. And there are some good news that in the Rhino 8 WAP, they are integrating Python, like the core Python, and it seems a little bit promising. But if you want to go further and further towards making your machine learning models and interface your tool through coding, scripting, working with cloud services for distributed training, then you are going to walk into the realm of a little bit more complex tools that are not convenient for a designer or a creative user. So you give a machine learning researcher it's Ubuntu server and the bash, they are going to be fine for the next 2 years, no problem. They never need any 3D environment like Rhino, Grasshopper, or whatever. So there is a bunch of requirements that doesn't let us directly go all the way to the end of this spectrum, but also somehow invites us to actually stay on the black box model. And then there are some like drawbacks for going more and more towards more detailed and more engaged with the machine learning model. When you're working with a black box model, like off the shelf, already available machine learning model, you don't need to get engaged with the details. You don't need to get engaged with the technical side. You can focus on creative application of it. You just need to work your Photoshop model picture or whatever. You don't need to get confused about like, what should I put here as the hyperparameter? Well, how should I set these things? But as you go towards a little bit more towards the developing learning algorithms, you're going to get more and more engaged with the tool making rather than making results and outputs. So this is a trade-off. If you want to make more custom-made tools with more level of, control over it, you are going to be a little bit more engaged with something that's not directly going to be your creative purpose. And here's the interesting part. When you're working with the black box models, it's limited. If you want to do something, you need to find somebody who has done that for you and you start using it. If not, there's no luck. And if you are super hardcore machine learning model, there's also limitation because you need to do something pretty precise, pretty specific, and it's also limited because of the scope of research you can actually do. So I was thinking, what would be the sweet spot for creative users and creative tool makers? And it's not on the black box model side. It's not on the developing learning algorithm side. It's something in between. And I think there's a distinction here between the creative users who are using machine learning models in their creative practices and creative tool makers who are making tools for such people. There is a gray area between these two, but I think in many cases when we are working, we may actually see there are two groups of people, creative users and tool makers. And I want to mention what is the difference between the tool makers and creative users. A tool maker, which I myself consider myself as a creative user, a creative tool maker, creates creative computing tools. It means that I develop some algorithms. I design the interactions. I also design the interface. Sometimes I need to design a hardware to work with it, and I implement all of them. And the purpose is to actually give the opportunity to creative users to use it to express their creative ideas. Either it's design, if it's going to be fabrication and making, or it's going to be performance. So there is a distinguishable distance between toolmakers and creative users. And this distinction between the two is actually not the best approach here, because if you study the process of toolmaking for machine learning, you realize that because of the fact that so many of the creative users are not equipped very well with the technical skills that are necessary to work with machine learning, there's an accessibility gap. For example, if a student who's not having the opportunity to take all those courses and guidance from people who are familiar with machine learning models and for example, Python programming language and all the libraries that are associated with it, there's an accessibility gap for those people. They cannot easily start working with these machine learning models because they don't have the knowledge. And then if they switch to work with these like black boxes that the toolmakers are making for them, there would be a lack of transparency. A creative user will not understand exactly what's happening in the background of the tool. And it means that they cannot hack their way around this tool. They cannot modify it for the case that they are interested in. And it's going to be a kind of like as the name stands for, the black box, it's going to prevent the person from take full advantage of the capacities of this tool. And this is something we see, for example, with Rhino and Grasshopper. When you work with Rhino, everything is in the interface. If it's there in the interface, you can use it. If it's not, you're out of luck. That's why we use Grasshopper, because it makes possible for us to get a layer inside, make our tool, and start working with them. And the last thing, which is really important here, which is basically the main topic of my research, but not the main topic of this discussion, is the abstraction gap. It means that when you're working with a machine learning model and you are not very well aware about the mechanics of it and the way it's working, and you're not capable of making your own data set, what you get is going to be something off the shelf, something not customized, and it's going to be completely abstracted from the environment, type of work, skills, and tools that you're using. So there would be an abstraction gap here. So my idea here was to actually see if it's possible to implement a situated approach into machine learning-based toolmaking in creative practices. And the idea is to actually make the tool with the user, for the user, collecting data from user, get that person involved in the process of training, and also get that person involved in the process of using it. So it's kind of like, rather than having a toolmaker and a user, I'm curious to know how it's possible to actually make a kind of like an overlapping and gray area between these two. So during the next part of this presentation, which I'm trying to keep it concise, I'm going to discuss 3 projects in which I try to start from a completely distinguishable toolmaker and user into a super hybrid workflow in which I collect the data from the user, I collect the data in collaboration with the user, train the model in collaboration, and eventually use it for a specific use case scenario. So the elements of things that you see in these 3 projects are accessible platforms, which is both familiar for me and those people, collaborative toolmaking, and using data as interface. I'll elaborate these 3 topics in the projects that I'm going to discuss them. So the first project that I want to talk about is Project Kivo. Project Kivo is the project that I've done when I was last at Autodesk Pier 9. And the idea was to learn a user-driven camera motion for robotic cinematography. If you're familiar with robotic cinematography, it actually exploded during the past 2 years because of pandemic, because you couldn't have so many crew in one room. It would be a good idea to have the camera controlled by a robotic arm. One actor here, record everything, then bring the other actor, record it, and the camera is going to make exact same motion. And it's actually pretty practical use case scenario, because in animations, they are also doing something like in hybrid movies, when they have animation and also actors, they are already using it in commercial, video cinematography. They are using it constantly. And the problem here is that defining these motions, the camera motions, is something that should be done by 3 stakeholders: the animator, the cinematographer, and the director. And this is such a cumbersome process that when we discuss it with the professional animators, they told us they usually do not even discuss it with the cinematographer and director. They just make a bunch of renders and a bunch of camera motions and render all of them, send it to the cinematographer and directors, and wait for them to respond, because it's faster to make like 10 renders rather than waiting for them to reply on one. So we were thinking, what will happen if we actually disrupt this process and see how we can actually get from this super smooth, almost machinic motions into something that represents or mimics the sorry for my sore throat, the motions of a cinematographer. So excuse me for that. So longest story short, we wanted to see if it's possible for somebody to start from a really basic motion and then use a machine learning model to actually learn the style of a cinematographer and modify that motion to get something like human-like or like specifically related to that cinematographer. So we came up with this pipeline. We said, okay, let's generate a bunch of samples from a cinematographer. Seems that it's serious. And then train a machine learning model based on that to learn these motions. And then based on that machine learning model, we can generate new samples and then send it to the robot to make more natural motions based on a user. So in this workflow, the creative users were responsible for generating samples. And then the expert, machine learning expert, which is in that case me, was responsible for making this machine learning model, training it, and then providing an interface for the user to actually draw samples, combine them, and then run it on the robot. So we actually made some tools to collect this data samples. So for those of you who are familiar with digital cinematography, this is a real over-shoulder red camera rig. And instead of having the red camera on it, we have an iPad that we could track in 6 degrees of freedom with enough accuracy. And you also find a couple of more ways to hold the camera, for example, on a gimbal, on a slider, or handheld. And we asked two people, Evan and Jason, to provide us with hundreds of samples of their camera motion. So I'm not sure if you can see it, but basically here you can see that Jason is generating a lot of samples moving around in a kind of a virtual object and make in camera motions. We also collected a couple of hundred from Evan, the picture in the middle left. And each sample of data looked like this. There was this image at the middle, this object at the middle, and they could move around it while looking at the iPad, because iPad could show what they were virtually looking at. Each sample was like 5 seconds long and 120 frames, because 24 frames per second multiplied by 5, I think that's 120. And at the end of the day, we had a couple of hundreds of these examples. Each camera here is representing one of the camera motions. And if this object looks familiar, I think this is the hero image, the hero object that you see in Fusion 360. I think it's actually a physical object, but we had the model of that. So the idea was to actually train an autoencoder model and pre-process data in a way that it actually represents that motion, send it to the autoencoder model, see if the machine learning model or the autoencoder model can actually learn the distribution of data and reconstruct it. The idea here was that it doesn't matter if we can learn the data. The good point about it is that we can actually manipulate that motion that we have, or we can actually start from one motion and combine it with another one, get some features from one, and then get some features from the other one, and combine them together to control a robotic arm. So the first step was to make a sanity check if this model can actually learn the motions. So we trained the model, fed the model with some test data, and we realized that the model is actually pretty good in understanding what's the motion and how it's actually moving across space. So the blue ones, the cyan ones, are actually the original motion, and the gradient ones are the one that were reconstructed. And the greener the color, it means that this reconstruction was more accurate. When we get into red or orange one, it means that it's a little bit less accurate, but they're acceptable for the purpose of this practice. We could learn the motion generated by that specific cinematographer, or like two cinematographers, and we could actually regenerate them. So I made this interface using Django, which is a platform, a framework for Python that let you make web-based interfaces. So the cinematographer or the animator could actually select some of the motions that they have already recorded. The plot on the left is actually showing all the samples that they provided, so distributed in 3D space based on their similarities. And they can select two of them, interplay between them, combine them, and see how is it possible to make a new motion. And then it would send it to Maya, and using the Mimic plugin, we could actually generate the code to control a robotic arm. So the basic idea was to find a way to learn a specific type of, style of, handheld camera motion from a user and see if we can generate a new one based on that. So we collected data from the user. I took care of the training, processing, and everything, and then the user could use it. So you see, like the cinematographer was interfacing me and the machine learning model through the samples of data. I was doing the whole development, making models and everything, and then the user would use it as a black box. So it's better than the previous ones, but a little bit, limited. So
Ardavan,
go ahead.
Just to give you a time check as
minutes?
requested. Yes, you have about 15 minutes. Yeah.
Okay, I hope I can finish the last part in like 10 minutes. Okay, so the second project that I want to discuss is a project that we call Secondhand. I've done this project as a part of my PhD thesis, and it was a part of the class I'm teaching, Introduction to Machine Learning and Design. So the idea here was to make a tool that generates handwriting typeface based on the data collected from the user. And I need to mention that here, the topic of interest was not generating handwriting. The topic of interest was integrating the end users in the process of making this tool and let them interface the model not only through a black box model, but also through providing data, interacting in the training process, and evaluation. So we made this data pipeline in this machine learning algorithm pipeline in which these students could generate motion sample, the handwriting samples. They could curate the data, train the models, and generate new samples. And I, as a tool maker, was the person responsible for making this meta tool, the platform and the framework. And those students could actually do the job. So, here, we actually did it in 2 rounds. In the first round of this study, we actually generated handwriting samples in like cells separately because it was way easier to, segment them. But in the second iteration, because we knew that it's impacted the handwriting quality of people, we decided to use the words collect the letters in words. So the results from the first round was something on the left, and the results from the second round of this data collection was something that you see on the right. And the point was that these students could generate data samples. Each provided us with a couple of thousand of samples, around 2,000. And there were like 15 students in the class in the 2 rounds of this. So we had something in the corner of 30,000 samples of data. And when it comes to making your handwriting tool, it might be a good idea to have more data and explore the possibility of combining different samples from different people to see how you can actually improve your handwriting samples just by borrowing something from your friends, or like combining and curating your data set. So students had access to web-based dashboard to curate data. So there were a couple of data visualizations here. So we were using Testing algorithm to distribute the samples based on their similarity, also based on their labels, like if it's an A, B, C, D. So students could actually watch every single sample pretty carefully and then combine them together in order to make their own data set. The machine learning algorithm in the backend was following the architecture of a variational autoencoder. My favorite model is variational autoencoder because of its efficiency, stability in training, and also its fast training workflow, because then students can actually train it without having access to a super fancy GPU. So in this case, I was using a variational autoencoder, a conditional variational autoencoder with convolutional neural networks as its layers. So I, as the tool maker, made this tool for them, fixed it, and told my students, okay, go ahead, bring your samples, data, fit this model, and train it. And if you want to know what's happening inside that model, it's a kind of like a visual representation of the variational autoencoder model. And students had access to interactive dashboards and notebooks to train the model. And their methods of choice for observing the process of training was looking at these plots and see how the input samples are translated into this model and then reconstructed back. And they could actually see the difference in order to monitor the process and figure out if it's a good sample or not. So students in this class in the first round had actually 4 weeks of training on like different fields of machine learning, a little bit more than 4 weeks of different, trainings on machine learning side. But in the second round of this class, we actually had a few weeks less than that. But students could handle it using these like interactive widgets, trained in the model, and then going to the latent space of that model and try to generate their own specific, letters one by one. So here in this platform, you can see that they have already trained the model. They are navigating the latent space, just like the way that, in the first example, Deep Cloud, the person was playing with those sliders to generate each letter that they wanted to do. And then they could actually use the other interactive widgets to render the text and make whatever they want. So compared with the previous ones in which the user just gave me the sample of data, I did the whole training and working by myself. In this scenario, the participants, the creative users, were making the data, curating the data, mix and matching it, and then training the model, and then sampling from it. So I was sitting back, provide them with a meta tool for them to make their own tool. So do you see that, like, the way they were interfacing the whole machine learning system is gradually changing from a black box into more and more integrated workflow? I think this was one of the good examples of like how much you can engage one user into the process. And you can see some of the examples at the end based on their handwriting, the second round of data collection and handwriting, and then mix and matching. And if you actually look at the samples on the right, you can easily recognize that there are more than one handwriting sample over there because they were mix and matching. And eventually they had access to this tool to actually render the text that they want using any single typeface that their friends and colleagues actually made. But the last project that I want to talk about today is this project that I'm right now working on. So this is santur, a Persian, traditional musical instrument. And I'm doing this project with a friend of mine, Mahtab Nadalian. And she's a professional santur player, and she's also a sound engineer. So the idea here is not to make a robotic arm that replaces her, but actually making a robotic tool that actually collaborates with her in a performance. And we are working together to generate data, train the machine learning model, implement the, fine-tune the model, and fine-tune the robotic workflow. So this is an ongoing project. It hasn't been finished, so I'm going to just report on the process until so far. So if you're not familiar with santur, but I think because we have a couple of Iranians here, they are familiar with this instrument. It's a trapezoid form, trapezoid box that's played with two very delicate hammers. And it has a bunch of strings organized in groups of 4, elevated by these bridges. And you played with, hammering each set of strings. So we were thinking, how can we actually learn the specific idiom of hair play and implement it in a machine learning model, train that machine learning model, then generate the command to control a robotic arm to actually play. So it's basically going to be in a duet with her. She provides the note, the robot is going to play it pretty close to what she does. So she is going to generate the playing samples, and then we are going to together pre-process the data, train the machine learning models, and then eventually generate the motions. So we are both going to be engaged in this process. I'll be going to be the barrier between like those technical shenanigans, and she is going to be the person who understands all the details, all the, for example, what is the correct action, what is the correct sound that should come out of this, because I have no experience on that side, and I have absolutely no experience in playing any type of instrument. So it's a kind of collaboration between me and her, and we are interfacing this model through, a collaborative workflow. And in order to collect the data samples, we actually find out that the best way to do it is use motion capture system. So these super delicate hammers are not capable of holding those, traditional markers that we usually see in motion capture systems. So we had to use tapes. So we made some prototypes, tested, and realized that these tapes are actually pretty accurate and pretty useful. So we went through a couple of data collection sessions. This is one of the early ones in which we actually installed the motion capture system. And as you can notice, it's actually here, and the motion capture was installed here until last week. And she played, I would record everything. And it was a little bit challenging because once you have these data, you need to do some post-processing and pre-processing for the model. So in this image, you can see that a bunch of motions of that hammers and the way they are moving in space in like around half a second. So we recorded everything in the speed of like 120 frames per second, and you see only 60 frames here. So you can see that it goes up, quickly comes down, and then comes back. And we need to actually make decisions about how much of data we need to have. So these motions here are each, for example, between 3, 4, 5, 6, or like 60 frames. And we know that obviously only 20 or 30 of these motions are enough. So if you look carefully at the data that we collected during that period of time, which in general, I think we have something in the corner of like 2,000 samples, you can see that different techniques, different hand gestures, even like the same technique, left hand, right hand, is totally different. And we need to do a lot of like, data processing in order to do it, to actually make it useful for a machine learning model. But I have no idea what does it mean. But she's the person who understands these techniques, the difference between left and right. And so I needed to make a platform and a toolkit for her to actually go through this data and annotate the data that it has and work with it and make it more accessible for the machine learning model. So if you want to see like how different the pieces of data that we have, if you look carefully on the left side of the screen, you see one sample. And here you can see those samples from one session back to back in like distributed in the length. And as you can see, they are not actually exactly the same. There are lots of variation between them. And if you just center them in the same corner that they are touching the instrument, you can see that they are all coming from different directions, different speeds, and diverging in different directions. So the data is concentrated, but it's really interestingly distributed across a wide range. And I'm going to finish in the next 2 minutes. So on the machine learning side, I decided to use my favorite machine learning model, variational autoencoders, conditional based on the left hand, right hand, and the node. But the point is, because I've never done this before, I need to figure out what would be the best architecture here. So I'm going to use multi-layer perceptrons, CNNs, RNNs, to see if we can capture the most information from the data. And it's actually a cumbersome process that's very technical. So I'm technically taking care of it by myself to make the best model. This visualization basically shows that the 200 different iterations and different architectures that I tested only for the multi-layer perceptron, there are tools that are automating it for you and making it way easier than it seems. So I decided like this model is the best right now in the MLP layers, but I'm right now working on the CNN layers and also recurrent neural networks to see which one is going to perform the best. But this project has also a robotic side. If we learn this distribution, these motions, we need to play it on a robotic arm. So I need to go through this process of making a holster to hold this tool because it's super delicate. If you look carefully at the end, I actually give it a shake and you can see that it's pretty delicate, and I should find a way to protect it from breaking. And right now the setup is like this. We are trying to figure out what will happen when we are playing these samples on the robot, because we don't want to break the hammer, we don't want to break the tool. But there are a lot of challenges here. As you can see, the speed in which the robot should move is pretty quick, and we're still not catching with the correct speed, and it's pretty shaky because it moves violently. And there are a lot of challenges on that side that I hope in the next couple of weeks I can actually overcome. So yes, that's it. It was the last project I want to share with you today. Thank you very much for your time, and sorry for going over time. I think I talked for 42 minutes. And if you have any question, you can actually shoot me an email, and some of my projects are actually available on my website, and you can have a look over there.
Great. Thank you very much, Ardavan. This was a fantastic talk.